I'm going to give you a couple of homework solutions from 1.7. I know this is perhaps a little bit one of the more weirder things that you're going to see in this course. Well, there is another one at the end, which is called proofs by induction. They seemed a little bit counterintuitive, and that's why the name contra is there, contraposition, contradiction, okay? You have to familiarize yourself with these kind of things, so I'm going to just go a couple of these. Number 9 says that use a proof by contradiction to prove, so the sum of an irrational and a rational number is irrational. Now, remember, I hope you went to look it up into the textbook, what it meant. Rational means that you're a fraction of two integers. Of course, the denominator cannot be 0. So that's rational means you're of the form m over n, where m and n are integers. We haven't... well, today we saw about sets, so I'm going to use my set notation, my freshly introduced set notation. If you have not seen it, then you go have to look at the video then. Okay, so these are integers, with n of course not 0. And irrational means not rational. It's just a negation of being rational. Very often, a way of making negation of a word is by putting in, or but assimilation, the in becomes, so the original form was irrational, or sometimes unrational, but it becomes assimilated as irrational. Okay, that's just language knowledge, but okay. So proof by contradiction, and so this is the first thing that we have to figure out here. What does that mean? A proof by contradiction is that you say this statement is not true. So suppose not, and when I say suppose not, I mean suppose that this is not true. And what I seek to do is, one way or the other, get something that is contradicting. So from assuming that the claim is false, I want to come with two statements. One statement says so, and the other one said not so, whatever that so is. So, and that is a contradiction. Okay, so suppose not. What does that mean? Well, if the sum of an irrational and rational is not irrational, that means that the sum of an irrational and a rational is rational. Okay? Or at least there is some like that. There is a number. So this says, if this is not true, remember, again, we speak about a number, an irrational number. Let's call this irrational number R. Oh, why is it doing this? So this is my R here. Let's call my rational number Q. Okay, and what it says is there is some, if you take an irrational number R and a rational number Q and you add them, then Q plus R is, that's what the sum is, Q plus R is irrational. That's the original claim. Now, the claim is again a little bit, it looks like a predicate again, because there are variables R and Q. Remember, what you actually need to do is we have to, you take a universal statement of that. Now, I'm going to not elaborate too much on that, but if I say that this is not true, that means I have a counterexample. So, suppose not means, what does that mean? There's an irrational number R, and there's a rational number Q, such that their sum, Q plus R, is rational. Okay. At this point, perhaps I'm a little bit stuck. I need to introduce, capture what it means to be rational or irrational. Which of the one can I capture best? Remember, negations, not rational, is something that's very hard to capture. So we would like to look at the positive things here. Rational, what does it mean? Well, I just said, it means that Q can be written as an m over n for some m and n that are integers. But there's something else that is rational, namely this sum is also rational. Is that the same m and n? No, there's no reason why they would be the same. In fact, they're probably not the same at all, right? So this means that there are Let's call them A and B, also integers. Remember, this is from our new lecture today. That is how we say it to be an integer. A, B is in Z, but of course B, A and B in Z, but B not 0, such that Q plus R is that fraction, is A over B. Okay, oh, but Q is M over N, so I should perhaps also put that. M over N plus R is A over B. What to do now? And there's always a part of the proof where everything is just writing down what you know. That so far we have actually, this is the part that you have to practice. You should be able to get to the part that I'm here. Because what I'm doing is just formally carrying out a proof by contradiction. Namely, I'm negating the statement, and I write down as much as I can what all these various objects that I now have look like. Okay, this is how far I can get, because R I cannot describe, because being not rational is something that cannot be described. Okay, so this is as far I get. So now some ingenuity has to come in. But what would you do here? Well, it is about R somehow. And remember, R is irrational, right? So why don't I solve for R in here? When you get equation, you're going to have somehow to solve this equation one way or the other. I'm going to solve for R. So solve for R. Why I do this, I cannot say. That is just my intuition. That is what I have to do. And perhaps, well, I can give you one hint, one explanation of why I'm concentrating on R. Because I already used how Q looks like, and I already used my information about Q plus R. The only information that I have not really been dealing with is information about R. So I want to know more about R, so that's why I solve for R. I hope this makes sense. How do you solve for R? Well, of course, you subtract from both sides minus mn. So minus mn, and here do also minus mn. So what we get that R is A over B minus m over n. But we know already that this actually on the right-hand side is a fraction. How do you do that? Well, put on common denominator. Let's call the common denominator here the common denominator. I'm not looking for the least common denominator. I'm looking just for a common denominator. That it would be b times n, right? So I'm going to multiply top and bottom with n here. And the second one, I top and bottom with what? B, right? Okay. So this is nb. Now I have the same common denominator. So this, I see that it is an minus mb over nb, or bn, doesn't matter. And so this is a fraction from our using the notation that we have from our course. We would write it this way, right? Wait a sec, this is a fraction. No. This means it's rational. This means it's rational, and I just said it is irrational. That's what I'm looking for. This is not a bad thing. This is a good thing. Remember, what I'm looking for is something that, oh, this is what I want. I want pink. I want something that says so-and-so is of this nature, and another thing says so-and-so is not of that nature. That is exactly what I want to be. This is the contradiction that I'm seeking. So here, these two things, I write this like it's a short chain. It's impossibility. Okay, so this is the contradiction. So what does that mean? Remember, if you assume that it was false and you get a contradiction, then it actually had to be true. That's how it works. Okay. And then the other question was number 17. No, number 18. Number 18. Number 18. So the statement is if 3... What is it here? If 3n plus 2 is even, then n must be even. You might try to do a direct proof, and you will see it's not easy. So we're going to do two things. 18a asks you to prove it by contraposition. And this is already something that we have to practice here. What is the contrapositive of a particular implication? Remember, if PQ is the implication, then this is logically equivalent to not Q implies not P. You negate both things, but you have to swap them. Okay, so this would mean, so the contrapositive, what does that say? That says that this is not the case if n is not even, but we call that odd, right? Then this is not the case. That's the P here. So then 3n plus 2 is not even, which again we just call odd. Okay, well, I want to get rid of the nots as quickly as possible. Now, n is odd. I know how to visualize that. Remember, n is odd means there is an A, there's a K, such that an integer K, okay, so I can write it a bit better. There's an integer or natural number. I think we're talking about natural numbers here. That was with this little n, with this capital N there. There's a K such that n is 2k plus 1. Twice a number plus 1 to make it odd. Twice would make it even, plus 1 makes it odd. So it is odd. Now once I have a form of this, I want to plug it in here. I don't want to, because what I need to show is, so again, what am I doing? I'm proving an implication. How do you prove an implication? You assume the hypothesis, n is odd. So we're assuming, so we perhaps write it down, assume n is odd. That's the hypothesis. And what we need to show 3n plus 2 is odd. Okay, this is how a direct proof works. We now, once we take the contrapositive, we go to the direct proof, right? So, and that is assuming the hypothesis, n is odd. That means that n is 2k plus 1. And now I have to show something about 3n plus 2. Well, let's figure out what we can do with 3n plus 2, because I have a formula for it. I can now replace n by this number. And what does this give me? If I work this out, it's 6k plus 3 plus 2. Okay. Now what is it I have to show? I have to show that it is odd. And how I do that, I have to write it in a form similar to this. Not by the same k, but something like that, meaning twice a number plus 1. Now, okay. Let's work this out. This is 6k plus 5. Now I have to split over 1. So I'm going to split over 1. 6k plus 4 plus 1. Why am I splitting over 1? Well, if it's odd, it has to have the 1 here, right? That I for sure have to have. So that's my 1. Now this has to be even. I have to write this as a multiple of 2, which I can do. I can factor out the 2. It has a 3k plus 2 plus 1. So first I do the, why do I split off the 1? Because I need an odd number. And then I verify that what is left is something where I can factor out the 2. And this tells me that it is odd. And I'm done. So this is a proof by contraposition. What is a proof of contraposition? You take your original implication, you take its contrapositive, and then you apply a direct proof. Now, the proof by contradiction is completely different. Well, complete is a bit strong word, but is different. Proof by contradiction. So we suppose it's not the case. Suppose not n odd. So sorry, 3n plus 2. Sorry, I have to go back to the original one, right? So let me. You see it there, the original one. Okay. So not 3n plus 2 even implies n even. Now let's think about this. I'm negating an implication. When is an implication? That means when is an implication false? This means that the hypothesis is true, but the conclusion is false. So it means that 3n plus 2 is even, but n is not even, therefore odd. That's my setup. Okay. And pardon the pun, oddly enough, the rest of the proof is now very similar, but it's something very strange is going to happen. So we can now mimic the previous proof. We have two numbers. In the previous proof, we had only one number we had information about. We had information about n is odd, and we needed to deduce information about this number. now we have information about both. We know that this is an even number, and we know that this is an odd number. Now I can write this even number, I can spell out what that means. But it's the reason, it's very hard to work with that, and that's the reason I didn't consider a direct proof. Because in a direct proof, I had this information, but I didn't know how to deal with it. That's why I went away from a direct proof. So although I have this information, at the moment I don't see how to use that, but this information is something I know how to use. I actually did that in the previous proof by saying there is a natural number n, and we're using our notation, new notation, namely that n is 2k plus 1. Now what I did next was then plug this in this number. So I'm going to plug this in, 3n plus 2. Why do I do that? Because that's the only other thing I have not used yet, right? So that is 2k plus 1 plus 2, which is 6k plus 3 plus 2, which is an odd number. And remember, why is that? I'm going to skip my little calculation. Remember here, this is the same calculation, right? We're dealing with the same number here. So we know that this is actually 2 times 3k plus 2 plus 1, which tells me that it is odd. You say, oh, that's good because that we wanted. No. What is actually really happening? And I said this is a little bit weird. We said that this tells me, let me write down here perhaps again what I just found here. So the conclusion is that 3n plus 2, 3n plus 2. Remember, this is an n and this is an m. I know I did it before and I didn't point it out to you. I'm sure everybody says the top one is an n and then the bottom one is something I don't know what it is, a bunch of hills. But that's how I write my n's and m's. I'm sorry, this is how I write it. It's too long. I'm too old to unlearn this. So you have to get used to that. Okay. Right, so 3n plus 2 is odd. Okay, so I have this. But wait. I have also this. Notice that these two statements contradict each other, and that's what I need. A proof by contradiction, I need a statement and its negation, both to be true, which is impossible. So now I get from this, I can conclude I have again a contradiction, which I remember is my flash, my lightning bolt, or whatever you call it, because we have a shorting. Okay, so this is contradiction, and therefore we're done. Okay, so the strategy is different, but the calculations are very much the same. And that is not surprise, because contrapositive and contradiction are very similar ways of proving things. Okay, I hope this worked. There's another one that I gave optional. I'm not going to do that. It's the optional one. I leave that for you to explore. Okay, these were the two problems that I assigned anyway.